This is my Calculus 1 course. Today we're going to learn how to calculate the area enclosed by two or more graphs. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. As usual, you're going to need these differentiation formulas. They're the most important thing for you to learn in this entire course, so if you don't have these memorized, take a screenshot. In previous classes, we learned how to find the area between the graph of a function and the x-axis. Today we're going to learn how to find the area between the graph of one function and the graph of another function. So here we have these red and green examples, and we have these purple bounds here, you could say. They're also graphs, they're just vertical lines. So we have four graphs. One vertical line, a second vertical line, the red graph and the green graph, and we're going to find the area between those graphs. If we want to find the area between two graphs that are above the x-axis, or the area between one graph that's above the x-axis and one graph that's below the x-axis, or if we want to find the area between two graphs that are both below the x-axis, it turns out we use the same formula in these three scenarios. That's this blue formula down here. We, in order to find the area, we find the value of the definite integral of the function whose graph is above minus the function whose graph is below, and obviously we integrate from wherever we want to integrate. These would be the vertical lines A and B, these vertical purple lines. And this formula only works if f, or the graph of f, is above the graph of g. Notice that in all these examples, the red graph f of x is above the graph g of x. Now you could use this formula if the graph of g of x were above the graph of f of x, but you would just have to modify it a little bit. You would have to do this orange work here. So let's say we write g of x first, and then we write f of x. Well, we would get the same area. It would be no different. There would be no difference whatsoever, except it would just be a different sign. So we'd have to put a green negative symbol there to counteract it. So it would be equal to that. But we're not going to do that because it's going to get kind of complicated. We're just going to write one formula, and you can easily modify that if you really have to. But we're not going to really worry about that in this class. We'll worry about that later on in the course. We don't want to make things complicated. Now, why does this formula work? Well, if you look at the y value of the red graph at some x value, and you look at the y value of the green graph at that same x value, I'll offset it a little bit just so you can see that. You can see that if we take the big y value and subtract the little y value, we get this this blue length here. And so if we find that blue length by subtracting g of x from f of x, that blue length can be considered the height of a rectangle. And we just add up a bunch of rectangles just like we do in the previous parts of the course. We just integrate from A to B, finding the areas of all those rectangles. So that's why this works. It also works in this situation. I know it doesn't seem like it, but this is the y value of the graph, the f of x at some x value, and the y value of g is actually a negative number. It's actually going in the it's going down. Now if you have a positive and you subtract a negative, well, that'll just give you a positive number. So if you take this y value up here and you subtract that y value, it'll give you the length from here to here. And so again, that's just the height of a bunch of rectangles we can add up, and we integrate and we find the area that's shaded. So the same formula works. We just find the integral of f of x minus g of x. The red graph minus the green graph. That formula that I showed you down here. Same situation, it's just f of x minus g of x. And in the third situation, we have the same thing. If you have a your y value for at some x value, that's the value of f of x. It's a negative number, right? And then the value of g of x at that same x value is a bigger negative number. So if you subtract this negative, or if you take this negative number and subtract a bigger negative number, you're going to get a positive number. And that positive number is going to be this blue distance, which again is what we want. Now that may not be as easy to see, but if you think about the logic of that, it works. And if we have those blue lengths, again, we can consider those blue lengths to be the heights of rectangles. And notice in all three of these situations, the heights of the rectangles were positive. So that means we don't really have to worry too much about our areas being negative. Now there are some situations where our areas could be negative, but today we're not really going to have to worry about that. So what if we have a situation like this where the red graph is above in these regions, but below in this region? What do you do there? Well, you could just integrate separately. But if you want to write an expression that represents the sum of the yellow and the blue areas, we'd have to use these pink absolute value symbols. If you wanted to write one expression, that is, as opposed to multiple integrals. Because if you add the yellow area and the blue area, the result that you get is not going to be the actual area of the yellow and the blue regions, because the yellow, or the blue area rather, is negative. Okay, and this is assuming that we're using our formula f of x minus g of x from a to b. A in this case would be here, and b in this case would be here. Again, if you use that formula, f of x minus g of x, the blue area would be negative because the green graph is above. So if you add the positive area and the negative area, you're not going to get the actual area of the yellow and blue regions added up, because the blue region is a negative area. So that's why you have to write absolute values, meaning when you get to negative area, it has to change to positive in order to add up all the area and make sure that it actually represents the area of those regions. The area of a region cannot be negative. There's no such thing as negative area. So, but we're not gonna worry about this today. You'll see that on the advanced placement test, but we'll cover that later on in the course. Okay, so I want you to get a picture of these differentiation formulas if you need them, and also get a picture of this information, specifically a picture of that formula. And again, we're not really going to use this stuff today. And let's do some practice problems. So we're going to find the area between these two graphs. So the formula that we're going to use is the integral of f of x minus g of x from A to B. That's the area between two graphs if f of x is a graph, or its graph is above g of x. Again, it only works if f of x is above g of x. And so let's plug in. Our bounds are these purple lines. We can also call those the limits of integration. And f of x is x squared, and g of x is negative x minus 2. So I want to be clear, g of x turned into this expression, and f of x turned into this expression. Now notice that we have to write parentheses. You see these parentheses? That's probably the part of this class that's going to cause some problems for students. If you don't write parentheses, then you're going to get the wrong answer. Students oftentimes have issues with signs. So now we have a double negative that becomes plus x, and a double negative it becomes plus 2. So all we have to do is integrate at this point. So the antiderivative would be 1/3 x cubed plus 1/2 x squared plus 2x, and we're going from -1 to 1. Again, we don't have to write the constant of integration. We don't have to write c, because c cancels out. Okay, so look at that and make sure that you follow what we did there. We used our formula, our master formula. Maybe we can color these limits of integration purple just so you can see that we plugged in those purple numbers. You don't have to do that. You don't have to color all these. Okay, so now we're going to go down here. We don't really have enough room up there, so we're going to have to move down here. So we're going to plug in 1 to that expression. And then we're going to subtract that very same expression with -1 plugged in. This is the fundamental theorem of calculus. And there you go. So all we have to do is calculate that. But let's go back and make sure that we plugged in all this stuff correctly. Don't do a lot of calculations before you first check to make sure that you plugged in everything correctly. Okay, so you can do this as fast as you want to do it. You don't have to show all the steps like I'm showing here. This is just basic arithmetic, really. At this level of math, you really should be skipping a lot of steps probably at this point when it comes to arithmetic, obviously. But I'm just going slower than I really need to go, just to help students to see what's happening with the calculations. Okay, so we have 1/3 plus 1/2 plus 2 plus 1/3 minus 1/2 plus 2. Now these signs, again, that's where students typically have some trouble. You got to be careful about what you're doing. Okay, so the 1/2 and the -1/2 looks like they cancel out. And we have 2 plus 2 is 4, and then 1/3 plus 1/3 is 2/3. So we have 4 and 2/3, and that is the area. So we found that the area of that shaded region. So there you go. We use this master formula again. Let's try number 2. So we're going to find that the area of that shaded region using the same formula, and we're assuming that f of x is bigger than g of x, or it's above. The graph of f of x is above the graph of g of x. That's the way it's going to be for every one of these problems. But for all we know, g of x could be written over here. It could be well, it doesn't really matter where it's written, but g of x could be above f of x in some cases. In this class, it's not going to be that way, but so we're going from pi over 2 to 5 pi over 4. And we'll make those purple limits of integration just so you can see where those numbers came from. And f of x is sine x plus 3. And g of x is cosine x plus 1. Now notice I use parentheses. You see these pink parentheses? I'm making them a bright color so you can see those. If you don't write those parentheses, then you're in big trouble, because you're going to get the wrong answer. It's so important to remember to write these expressions correctly. Okay, so we have sine x minus cosine x, and maybe I'll go slow here. We're just distributing the negative, and we're simplifying the integral. So we have sine x minus cosine x plus 2. All right. And now we're going to find the antiderivative. So the antiderivative of sine is negative cosine x. Antiderivative of cosine is sine x. Antiderivative of 2 is 2x. And we need our brackets and our limits of integration. Again, we don't need to write c. We don't need to write the c value, because c just cancels out when we use the fundamental theorem of calculus. Okay, so let's double check this. Everything looks right. So now we're going to plug in 5 pi over 4 to our expression. And then we're going to plug in pi over 2 to the same expression and subtract that whole thing from what we wrote. Alright, so let me find some more room. Or just scrunch that in. So let's go back and double check to make sure we wrote everything correctly. It's very easy to make a mistake. So don't just assume that we wrote everything correctly. Seems like everything is correct. And now all we have to do is simplify and we're done. So again, you can look over what we did so far and compare it to the previous problem. Now, these are angles where we can use triangles to help us calculate them. And these angles over here are angles where we have to use the sine and the cosine curves. So let's start with the blue angle. Now, because we have a pi and we have no degree symbol, that's a dead giveaway that we're dealing with radians. In calculus, as I said, we mostly deal with radians. And so we need to know what 5 pi over 4 is, but a lot of students may not know. And the surefire way to to know is to multiply by your conversion factor, 180 degrees over pi. And you don't have to put radians because there are no units for radians. And the pi's cancel out. Long story short, you get 225 degrees. But another way to do it is to remember that pi is 180, so you can just replace pi with 180 degrees. Do the math on that, and again you get 225 degrees. But to be honest with you, the way that I do it is I remember that pi over 4 is 45 degrees, and if we multiply that by 5 times 45 is 225. So there's a lot of different ways to do it. So I'm going to rotate 225 degrees, and then I'm going to draw the triangle, and of course we need to know the reference angle. Without the reference angle, we're just lost. So we can see that this is going to be a 45, 45, 90 degree triangle, and if you know your 45, 45, 90 degree triangles, which you should by now, that's just basic trigonometry, you know this side is negative x, and this side is negative x, and this side is x root 2. Now again, it's common for students to be rusty with their trigonometry. That's not uncommon at all. But at this point in the curriculum, you really need to pick this up quickly. You need to know your 45, 45, 90 degree triangle and your 30, 60, 90 degree triangle. Okay, so cosine of a 225 degree angle can be calculated using that triangle down there. So cosine is the adjacent side divided by the hypotenuse. So we have negative 1 over root 2. Sine is the opposite side divided by the hypotenuse, which gives us the same number, negative 1 over root 2. And we multiply, we get 5 pi over 2. Now over here with these yellow angles, we need to use the cosine curve. Why is that? Because if we try to find the cosine of a 90 degree angle using triangles, you're going to run into some problems. Here's the triangle for maybe 30 degrees, here's the triangle for 45 degrees, here's the triangle for 60 degrees, and here's for 70 degrees, and then 80 degrees, and then what happens with 90? Well, the triangle just disappears, it collapses. There's no triangle. So you can't use triangles to understand that. Now some of you may be using the unit circle. If you use the unit circle, you want to look at these points. Remember that circle, and you have your different points. If that's the way you learned it, then you need to get out your unit circle. But in my curriculum, we don't really do it that way. But if you use the unit circle, that's completely fine. So we need to use the cosine curve. So that's the cosine curve. I guess I can use yellow for that. It doesn't really matter what colors we use, but so if you recall, pi over 2 brings us down to here, and you can see that the y value of that point is 0. So cosine pi over 2 is just 0. Now sine, we need to write the graph for sine, and you can see when the angle is pi over 2, the y value of this point up here is actually 1. So sine pi over 2 is actually 1. We multiply these, we get pi. So I know it seems like this is taking a long time to do this, but you're going to be expected to do this in your head, to be honest with you. You're going to be expected to do all that in your head, and that's a lot for a first year or a first course calculus student. But I'm just letting you know that that's what you're expected to do. You're expected to know how to do that stuff quickly. But I'm just giving you a little bit of trigonometry review because the reality is that students typically don't really have that stuff down as well as they should. But just remember, you're going to have to know the 45, 45, 90 degree triangle and the 30, 60, 90 degree triangle, and you're going to have to know how to move those triangles around in the different quadrants based on the angle. And you're also going to know, you need to know the graphs of the sine and cosine curve and the tangent and the cotangent and cosecant, secant, and so on and so forth. In calculus, you're going to be expected to know all that. And I know what you're thinking. You're thinking, that's not fair. I don't want to have to know all that stuff. Well, this is calculus. You can't escape this. There's a lot of stuff to know in calculus. That's why it's considered such a huge topic. Okay, so we have this expression here, and we can combine the pi expressions if we want, I guess. There's not really much more that we need to do. We can make that 3 pi over 2, but I would just allow you to leave it like that. That's the exact answer. You don't really have to write the decimal approximation, although most people would probably come up with a decimal approximation. You don't really need to do that. Okay, so now it's time for you to try. So you're going to use the master formula over here and here. And for these problems, we're assuming that f of x its graph is above the graph of g of x. So I'm going to give you one more chance to take a picture of these formulas and to take a picture of this information here. This formula is really the most important thing. And I want you to take a picture of these problems here and maybe get a picture. Well, you're not going to need that trig right now. But get a picture of those problems. Now, your final answer is going to have trigonometric expressions. I forget exactly what it's going to be. It might be cosine or sine. And you're not going to be able to use triangles or the graphs of the cosine functions or the sine functions to calculate your answer. If you have something like this, 3 pi over 2, you don't need a calculator. But if you have something like this, where you just have some random number like 3.2, or maybe you have like sine 1, well, you can't calculate that without a computer, your TI-84 plus or whatever you're using. So that's the situation, and if you want, you can come up with a decimal approximation, or you can just leave it with cosines or sines. So just be aware of that. That's the warning that I gave you over here. So try number 3. When you come back, we'll do it together. So I'm going to write the master formula for you when we're trying to find the area between the graphs of two functions. Assuming that f of x, its graph is above the graph of g of x, we're going to use this master formula. So try number 3. When you come back, we'll do it together. So you can leave your answer like this if you want, but when you have such a weird expression, it's probably better to come up with a decimal approximation. But you need to make sure that your calculator is in radian mode. It's so common for students to try to calculate something like this, and they don't realize that these blue numbers are not degrees, they're radians. So if you're using a TI-84 plus, push the mode button at the upper middle left, and then use the arrow key to make sure you're on radians. Press enter on radians, and the blue button, and then the mode button again to quit out of that. If you're using a different calculator, then there's some way to figure out if you're in radians, which you call rads, or degrees, which calculators often notate with a DEG, or they abbreviate with a DEG. So I'm going to enter 13.5 first, and then plus sine 2, enter, and you can do this step by step, or you can try to enter the whole expression in at once, but just be aware if you enter the whole expression in at once, there's more of a chance that you're going to get the wrong answer. Because it's very easy not to enter the expression correctly, but you should get somewhere around 15.25. Okay, so if you got that right, excellent. The problem doesn't tell us what to round off to, but common sense tells us that 15.25 is a pretty good number to round off to. Now I want you to try number 4. Be aware that you have to use differentiation formula number 9. So you have to use this formula here because we have an exponential expression. But this is going forward, you're going to be going backwards. So you have to use that formula, but in your head you have to understand how we would go backwards. Instead of multiplying by the natural log of your base, you're going to divide by the natural log of your base when you find the antiderivative. So go ahead and try number 4, and when you come back we'll do it together. Okay, we're back. So if you came up with a decimal approximation, good. If you got this expression, good. If you stopped here, like I said, and just found your decimal approximation from here, that's fine. You don't have to simplify all the way down to this. So you can check, calculate, see if you got the same decimal, convert this to a decimal and compare it. So if you got that right, excellent. Okay, so we're going to do the next problem together. These problems are entitled Finding Limits of Integration. Why do we have that title? Well, because notice that there are no purple equations over here. In the previous problems we had these purple lines or segments, and we had these purple equations showing us the limits of integration. But in the next problem we don't have that. But we're still supposed to find the area that is bounded by the graphs of these functions, and so we need to know where to start our integration. What is A and B, the limits of integration? Well, you can see just by looking at this area that we have to start wherever that point of intersection is and end wherever this point of intersection is. So I need to find the x values of those points of intersection. Now we can see what the x values here are. It's pretty obvious that it's -1 and 1. But technically we don't know that for sure. It could be a little off. I mean, we can't really trust the graph, and more importantly, in most situations you're not going to be given the graph. You're going to be given the equations, you're not going to be given the graph. And so the reason I'm drawing the graph for you is I'm just trying to, we're trying to understand the concepts here. But just be aware, in most problems you're going to be expected to figure this out, and if you have to draw a graph to figure it out, you're going to be expected to do that yourself. Okay, I've just pre-drawn these graphs so that we don't have to waste time graphing. But we don't know what these points of intersection are necessarily if we're just given the equations. So how do we find the x values where we start our integration and end our integration? Well, when two graphs intersect, that means that the points of intersection, those coordinates are common to both equations, meaning the x values at those black points are the same for the red graph and the green graph. And at this point, the x and y values of the functions are the same for the green and the red graph. So we're looking for the x values, but the way that we find the x values is we set the y values equal to each other. F of x is the y values of the red equation, and g of x is the y values of the green equation. So f of x is negative x squared minus 2, and g of x is x squared minus 4. And so if we solve this equation, we find what x values make the y values equal. And those x values are going to be what we're looking for. So we're going to add x squared to both sides. Then we're going to add 4 to both sides. Then we're going to divide both sides by 2. Then we're going to square root both sides. Now, there's probably 3 mistakes that students make in the curriculum. They're the most common mistakes. One mistake is they think that if you have the square root of a squared plus b squared, that equals a plus b. That's one of the biggest mistakes. The second biggest mistake, or one of the 3 big mistakes, is they think that negative 1 squared is the same thing as negative 1 squared with parentheses. That's not true. And the other mistake they make is that the last of the 3 is that when they square root both sides of an equation, they forget to write plus or minus. So be aware of that. Okay, so those are going to be our limits of integration, and I'm just going to write that in an expanded form so that that's clear. X can be negative 1 or x can be positive 1. So at this point here, x is positive 1, and at this point x is negative 1. So that tells us what the limits of integration are. We can draw vertical lines there if you want to help you, but you don't have to. Okay, so there's our master formula. We're going to write negative 1 and positive 1. Just to drive the point home, I'm going to make these purple. I'm going to make these purple. You don't have to use colors, of course. So we have f of x, and we're going to subtract g of x. Right? So we have negative 2x squared and plus 2. And then we get negative 2/3 x cubed plus 2x from negative 1 to 1. So we have negative 2/3 1 cubed plus 2 times 1 minus negative 2/3 negative 1 cubed plus 2 times negative 1. And we don't have a lot of room to do this, so I'm just going to combine all this stuff. Or maybe I'll show a couple other steps. So we're going to get minus 2/3 and plus 2 if we do that quickly. So it looks like we get 4 minus 4/3, and that's going to be 2 and 2/3. So there was an example where we had to actually find the limits of integration. In the limits of integration, we're going to be the x values where the graphs intersect. So let's do another example. We have to find the area of the region that you see highlighted there, the yellow region, but we don't have any purple equations here that tell us the bounds. Now again, we can just look at the graph and say, well, of course it's going to be negative 2 and positive 2. We're going to integrate from x equals negative 2 to x equals positive 2. But what if you don't have this graph? In most situations, you're not going to have the graph. So we're going to have to find where the graphs intersect. So we're going to have to set the y values equal to each other and solve for the x values. So f of x is 2, g of x is x squared minus 2. We have to solve for x squared, add 2 to both sides, and then square root both sides. Now again, when we square root both sides, students forget the plus and the minus. So it's just a given that students are going to forget to do that, and that's going to cause you problems. So I'm just warning you now. It's very easy to forget that. Okay, so now we know that the x value at this point is negative 2, and the x value at this point is positive 2. Even though we have the graph, we don't know that for sure. Again, there's no guarantee. Only by solving the equations can we know for sure. So that's another reason we do it. We do that. So here is the master equation for today's work. So we're going to integrate from negative 2 to 2. F of x is 2, and g of x is x squared minus 2. Okay. So we get negative x squared plus 2. And that's going to be 4 minus x squared dx. So the antiderivative is going to be 4x minus 1/3 x cubed from negative 2 to 2. Again, we don't need to write the c values. The constants of integration, they always cancel out. Okay, so we're going to plug in 2 to our expression and subtract the same expression except with negative 2 plugged in. And we have 8 minus 8/3. We have negative 8 minus 1/3 times negative 8, and we don't really have enough room to show every single step here. But looks like we're going to have 16, and the 8/3 looks like they're going to cancel out. Well, actually no, we're going to get minus 16/3. And so we're going to end up with 16 minus 5 and 1/3, it looks like. And that's going to be 10 and 2/3 is our final answer. So you don't have to show every single step of this arithmetic. You can go a lot faster. I'm just slowing down for your sake, but if you don't need to see all that arithmetic, then by all means, speed up. Do as much of the arithmetic in your head. You don't have to show arithmetic in calculus. All you have to do is show a little bit of the algebra and the basic concepts of the calculus, the master equation, and so on and so forth. Okay, so now it's time for you to try. Get a picture of these two problems, and I want you to try number 7. We're going to use the same formula. The area of that shaded yellow region is the integral of the function whose graph is above minus the function whose graph is below from a to b. So try number 7. When you come back, we'll do it together. So take a picture of these two problems and use them to help you with number 7. Now, in order to find the limits of integration, we have to solve for the x values of the points of intersection. In order to do that, we have to set the y values equal to each other and solve for x. Then we're going to use our special formula. Area is equal to the integral of f of x minus g of x from a to b, and this equation up here is going to tell us what a and b are. But just be aware that a lot of students, even at the college level, a lot of students have trouble solving this equation. In order to solve this equation, I'll give you a hint. You have to use your GCF factoring. Remember, we talked about that at the beginning of this course. You have to know the three types of factoring: quadratic factoring, difference of two square factoring, and GCF factoring. So see what you can do. If you get stuck, that's okay, but yeah, there's a lot of students don't get stuck trying to solve this equation, but it's and some students will find one answer to the equation, but they won't find the other answer. There's two x values. There's one here and there's one here. So see what you can do. If you can't find both x values, then you'll see the work after we perform it. So try number 7. When you come back, we'll do it together. Okay, we're back. Looks like 1.5, or you can write it as 3/2, however you want to do it. Okay, so if you got that right, excellent. So the part that students really have trouble with is this blue part right here. See that? A lot of students forget how to solve an equation like that, or maybe they just were never taught how to. In my curriculum, you learn that, but it's easy to forget what to do there, so don't feel bad if you forgot how to do that. Just put everything on one side and factor your GCF, and then you can see the two solutions. Okay, so I want you to try number 8. Number 7 will help you. Again, if you haven't gotten a picture of numbers 5 and 6, get a picture and use number 7 to help you with number 8. Again, we don't know the limits of integration. You have to set these functions equal to each other and solve for x to figure out where we're going to start and end for our limits of integration, the limits being a and b. Try number 8. When you come back, we'll do it together. Okay, we're back. 5 and 1/3. So if you got that right, excellent. Okay, so now we're going to do problems that require the substitution rule. Now, I know you don't really want to do problems that require the substitution rule, but they're everywhere. You're going to have problems where you have to use a substitution rule, and there's no avoiding it, so we have to do some of those problems. So here's an example. We're going to do the same thing we did before. Luckily, we have our limits of integration. We don't have to solve for the intersection, because if you look at this picture, we see those purple segments there. They show us what area we're finding. So I'm going to write my formula. You don't have to keep writing this formula over and over again, but I'm just going to write it just so we know what we're using. And so the limits of integration are 1 and 2. And f of x is 1 over x squared minus 1. And g of x is, I'll use a bracket, x minus 2 cubed minus 2. You don't have to use brackets. You can just use another set of parentheses. It's up to you, but brackets may make it easier to see what we're doing. Okay, so let's simplify the expression. We're going to need to change this to x to the negative 2 power before we integrate, so might as well just do that now. We need to distribute the negative So that changes those signs. And we can combine these blue numbers. That just becomes 1. So we're not going to have any problem integrating these terms here. We've done that many times, but if we try to integrate this, you may come into some problems. Now, you could probably do this without using U substitution, and it's fairly obvious what the answer is going to be, because this is somewhat easy expression to find the antiderivative of. It's going to be x minus 2 to the 4th power or something like that, right? But just to practice our substitution, let's go through it. Now, if we let u be x minus 2, then technically, if we're going to change this into a du integral, we would have to modify these expressions too. So, and it's not really going to work. U substitution only works when you have certain expressions. So what we need to do is we need to use this formula up here, the integral of a sum property. We're going to break the integral into a bunch of different integrals, because we have a sum of a bunch of expressions, and we're going to break it into a bunch of different integrals, so we can use U substitution on just one of the integrals, this integral here, or that expression, rather than have to work with it on the other expressions. So we have the integral of x to the negative 2 plus the integral of 1 plus the integral of negative x minus 2 cubed. And you can take this negative out if you want to. You don't have to. Remember, that's this principle here. You see the pink C? If you have a constant, a GCF, something that's common to all the terms, you can just pull it out of the integral. I usually do that because I like the expression in the integral to be as simple as possible when we find the antiderivative, but you can also leave it in there. That's fine. So, we need to now use U substitution on this. We can find the antiderivative of that really easily. It's just going to be x to the negative 1 with a negative in front of it, and 1 to 2. And this is just going to be x, 1 to 2. But what about this? That's the problem. So we'll do U substitution over here. We don't really have a room on the page over there, so we're going to let U be x minus 2. We don't really need parentheses. And step 2, we're going to find the derivative. Step 3, we're going to solve for dx, but dx is already solved for. And step 4, we're going to rewrite the integral. So we have negative u to the 3rd power du. And in step 5, we're going to cancel out the x's, but you can see that there are no x's to cancel out, so there's nothing really to do there. In step number 6, we're going to find the antiderivative, and that's going to be negative 1/4 u to the 4th power plus c. And in step 7, we're going to replace u with x minus 2. Okay, so that is the antiderivative. It's negative 1/4 x minus 2 to the 4th power from 1 to 2. Now, we're not allowed to have a plus symbol next to a negative symbol like this. So what we really need to do is write a bracket there also. Sometimes you do that. You not only write a bracket over here, you'll write a bracket here if you need to. Now, we don't need to do that. What we could do is just get rid of that plus sign and just move this whole thing over. That would probably be best. But I'm just going to leave it like that so you can kind of see that that's something that you can do. Now, all we were looking for is the antiderivative of this expression up here. And we found it. But we did it in parts. Now you can do this. You can do each one of these expressions at one at a time. This one, and then this one, and then this one. But that would be kind of tedious. It might be kind of confusing. So what I'm going to do is I'm going to just recombine everything. And you're going to get the same answer. So what we did is we found the antiderivative of this expression here, which is that. So we found the antiderivative of that, and we got that expression down there. Okay, so now we're going to look for the final answer. But we don't really know what to do with this, so we have to change it to negative 1 over x. And now we can plug in the numbers. Actually, we're plugging in 2. So plug it in 2. Then we're going to subtract the same expression with 1 plugged in. And there you go. Whatever that ends up being, that's going to be the answer. But we're out of room, so I'm going to copy this and bring it up. And before we do that, let's check and make sure that we put everything in there correctly. Most students don't want to check, they just want to go forward. But if you do that, it's pretty much a guarantee that you're going to get the wrong answer. So over time, you learn to double check your answers over and over and over and over and over again. It makes things go a little slower, but at least you get the right answer. Okay, everything looks right. So we have negative 1/2 plus 2 minus 1/4 times 0 to the 4th minus negative 1 plus 1 minus 1/4 times negative 1 to the 4th. You don't have to show every one of these steps. We're going really slow here. This obviously goes to 0. We have negative 1/2 plus 2 minus well, these two terms, add them together, you get 0. And negative 1 to the 4th power is just 1. Again, I'm going a lot slower than I really need to go. And we have 1 1/2 minus negative 1/4. And looks like we have 1 3/4. So in that problem, we had to use substitution. Again, we can't really avoid substitution. It's going to be all over the place in this course and pretty much every calculus course that you take. Okay, so let's try one more of these together before you try one on your own. I know these are kind of tedious, but we only have 3 more problems today. This problem, and you're going to do 2 problems. So, Now again, we're given the limits of integration. Now we should probably draw those graphs. Let me just draw those. That way we can see the area we're looking for, even though we really have it. In this situation, it's kind of weird. So we can see that the intersection point is where the area starts. See this intersection point? But in this problem, we're not making you actually solve for the x value at that point. They're giving you the limits of integration just to make things easier. So technically you could graph those lines, but actually I'm just going to leave them off. So we're going to do the same thing that we did before. It's no difference. We're going from -3 to 0. F of x is root x plus 4 minus 2. We're going to subtract g of x, which is x plus 5/3 squared minus 2 7/9. Okay. So we just have to simplify that expression. I'm going to distribute the negative. And then we're going to combine these blue numbers. So -2 plus 2 7/9 is 7/9. Okay, so in this situation, you see we're going to have to use U substitution here and here. We don't want to use U substitution with the integral compact like this and with one big expression, because if we let U equal x plus 4, right? Well, that means that U cannot be x plus 5/3. So, I mean, we don't want to do this as one integral, so we're going to break it up into 3 integrals. That'll just make it easier for us to understand what's going on. Okay, so everything looks right. Now, here again, we're going to use U substitution. So I'm going to go over here. I'm going to let U equal x plus 4. And second step is to find the derivative of U. Third step is to solve for. Fourth step is to write the integral. So we have root U du. Fifth step is to cancel out the x's, but there are no x's, so that was easy. Step is to find the antiderivative, but remember, we can't find the antiderivative if we have a root, so I have to change it to u to the 1/2 power. So we get 2/3 u to the 3/2 power plus c, and then we're going to plug in u, which is x plus 4 to 3/2 plus c, and we don't really know how to interpret the expression unless we change to roots. So let's change to roots. So we have 2/3 square root of x plus 4 to the 3rd power plus c. And so we're going to change that to 2/3 square root of x plus 4 to the 3rd power from -3 to 0, and then we can go ahead and find the antiderivative of that. Might as well. That's easy. That's going to be 7/9 x from -3 to 0. But now we have a problem with this. We have to use u substitution on that. So I'm going to use purple for that. And we're going to go over here. So we're going to let u equal x plus 5/3 dx. Step 2. Dx is already solved for. And then I'm going to write the integral with u, in terms of u. And then step 5 is to cancel out the x's, but there's no x's to cancel out. Step 6, find the antiderivative. And then step 7 is to plug in what u is equal to, which is x plus 5/3. So there you go, that's the antiderivative. Okay, so x plus -1/3, and we're going to need to write a bracket so we don't get confused here. So -1/3, we're not allowed to write a plus symbol next to a negative, right? So bracket's going to be good to write there. So -1/3 x plus 5/3 to the 3rd power. From -3 to 0. So now let's go back and check all this, make sure we did everything right. So I'm finding the derivative of each term in my head, and everything looks correct. It's always good to go back and find the derivative of each term. Now again, we could do this piece by piece, but it seems simpler just to combine everything, recombine everything. You don't have to recombine everything. You can just, again, do it piece by piece, but I think it's better to combine it into one expression. So just to make it very clear, we found the antiderivative of this blue expression, and we got this expression here. but we had to do it, we had to break the integral into parts so we could use substitution. Because if we didn't do that, then it would get kind of confusing. Okay. So again, double checking everything, making sure everything is correct. Now let's plug in 0 to our function. And then we're going to plug in -3 to our function. Sorry, my computer's going kind of slow here. And we're going to subtract these two expressions. Let's make sure we have this all right. So we have -1/3, -3 plus 5/3 to the third power. And let's see if we can fit all that onto the same page. There you go. So you don't have to show all this. You may think that what I'm doing right now is really tedious and is just taking too long, but you don't have to show all this basic arithmetic. You can do a lot of this in your head. So just be aware of that. So let's simplify, but before we simplify, again, let's double check everything, because there's a lot of stuff going on here. If you make a mistake, it's going to be a lot of work for no reason. So we need to kind of, well, we still need to show some of this, I guess, for students' benefit. Then we have 5/3 to the third power. And the square root of 1 cubed minus 7/3. 7/9 times -3 is -7/3. And we get -4/3 to the third power. Okay. Or -4/3 to the third power. And we have 2/3 times 8 minus 1/3 times 125 over 27 minus 2/3 times the square root of 1, and so on and so forth. This is going to be -64 over 27, and obviously we're out of room. So again, I just want to stress that I'm showing a lot more work than you really have to show. I just want to make sure that you see exactly what's happening. So we're going to copy this. And so let's see if we can simplify this. We're going to have to kind of rush through because we're running out of room. So we have 16 over 3 minus 125 over 81 minus 2/3 minus 7/3 minus, let's just say, plus 64/81. And rushing through this, we get 16/3 minus 125/81. I'm going to go ahead and combine those two fractions. So 2/3 minus 7/3 is negative 5/3. And plus 5/3 minus 64/81. So we can combine negative 125 and negative 64, and we get negative 189. We can add 16/3 and 5/3 and get 21/3, which is just 7. And 81 times 2 is 162. Remainder is 27. So we have 7 minus 2 and 27/81. But that's the same thing as 7 minus 2 and 1/3. And then we get 4 and 2/3, it looks like. So I know that was a lot of work, but believe it or not, in calculus you're going to be expected to do some of these types of problems. In fact, quite a few of these. So now it's your turn. So get a picture of the substitution rule so you can remember how to do that. And these formulas at the right, and then get a picture of this problem and a picture of this problem. And I want you to try number 11. Now we're given the limits of integration, so you don't have to set the equations equal to each other. Remember, if you have to use u substitution on one expression to find the antiderivative, then you have to separate the integral if you have other x values in the integral that are not going to be part of that u substitution. So I'm going to write your formula here. You probably already know this. It's pretty simple formula. But remember, our area is equal to the integral of f of x minus g of x from a to b. So try number 11. When you come back, we'll do it together. Okay, we're back. Okay, so if you got that right, excellent. You can take a picture of this information if you want to. If my computer will speed up here, take a picture of that problem. And in the next problem, I believe you're going to have to do 2 u substitutions, like number 10. So, and remember, if you come up with the natural log of a negative number in an integral, it's okay to just change that negative number to a positive number. Normally, when you have a negative number in a log, that's considered to be an undefined expression. But when you're integrating and you come up with the natural logarithm or any logarithm, you can just turn that negative into a positive, and it'll give you the area. I know that's kind of strange. You don't need to know exactly why that is, but it will give you the area if you just change to a positive number. Also, you have to use formula number 12. So let's go look at formula number 12 real quick here. So the derivative of natural log x is 1 over x. You need that. Okay. So try number 12, and when you come back, we'll do it together. Alright, we're back. So there you go. You can calculate the decimal value of my answer and compare it to the decimal value of your answer if you didn't get the same form. But notice that we changed the negatives in the logarithms to positive numbers. And notice that the value of natural log 1 was just 0. Remember, natural log is log base e of 1. And if we set that equal to a variable, say y, and translate to an exponential equation, we can see the only value of y that would make that equation true is 0. So y, which is what we're looking for, is 0. Y is log base e of 1, which is natural log of 1. So if you got that right, excellent. If you didn't get it right, that's okay. There's a lot of ins and outs in that problem, so if you made a mistake somewhere, that's okay. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2 and number 3 and number 4 and number 5 and 6 and 7 and 8 9 10 and 11, but don't go before you get your homework. Let's look at the homework. Here's screenshot number 1 of the homework and number 2 and number 3 and number 4 and number 5. But don't go before you get the answers. Here's the answers to the homework. It's not enough to just attempt the homework, it must be done correctly. So get that homework done completely, correctly, neatly, and keep it in order in your binder. And I'll look forward to seeing you in the next class.